So let's dive in. So our last unit is sticking with heat transfer, and we're going to talk about convection now, which is really kind of the marriage of heat transfer and fluid mechanics, because convection is heat transfer that involves a fluid that moves, right? So what we're going to do is we're going to also look at the differential form of heat transfer, just like how we did for conduction in the last unit. But we're going to do it for convection. Okay, so to begin this, I just want to quickly compare and contrast convection and conduction. Both convection and conduction require a medium. Of course, radiation does not. We're not talking about radiation in this class, I'm afraid. So I will leave it at that. Solids can transport heat via conduction, but not convection, because in a solid material, the molecules or the particles in it don't flow relative to one another. So molecules don't flow relative to one another. This should be 3, and this is 4. Convection requires movement or flow of the material. And so because of that, liquids and gases can flow relative to one another. So therefore, for a liquid and a gas, heat can be transferred by diffusion, which is another way of saying conduction. And advection. So this is transport due to fluid motion. And so diffusion and advection you can think of in terms of heat transfer. You can also think about it in terms of the transport of any other kind of material. So if you had, for example, a bucket of water and you put a drip of ink in there, the ink will disperse via diffusion. So that's random molecular motion. It'll also disperse via advection if the water in the bucket is down. So if you're sloshing it around or you stir a spoon, it'll transfer faster, right? So we can think of convection as the heat transfer that involves both heat diffusion as well as advection. In this, it's split into parts. We're going to external flow convection. So this is like flow over a plate, for example. And then the second part is going to be internal flow. So this is like flow through pipes. Okay, so let's start with external flow convection. And we're going to start, kind of with the basics that we went over in the heat transfer unit a while ago. And so when we were reviewing what you learned in previous class, we know that the rate of heat transfer due to convection is proportional to the surface and fluid, and they are related to each other by Newton's law of cooling. All right, so we have Q dot of convection. So the rate of heat transfer due to convection that's this Q dot convection. All right. And just to remind you, the lowercase q is going to be the total rate of heat transfer divided by the surface area. And then obviously we have the temperature difference between surface and the fluid is this Ts minus T infinity term. And then we also have a convection heat transfer coefficient. All right. When we talked about this last time, I made mention of the fact that H is not a material property. So that means that inside of a control valve, we have to write this a little bit differently. So we are going to write this as an average H bar. So this could vary over space. And that's because it's not a material property. So the bar is an average. Or an average over the area. Okay. So in general, H, the convection heat transfer coefficient is a function of space. It's time if it's an unsteady flow. And so anytime the flow conditions change, H could change as well. All right, let's talk a little bit about boundary conditions. So we saw in the previous unit that heat transfer has an equivalent boundary condition to the no slip condition that fluids. This is called the no jump condition. All right, we talked about this before. So anywhere a fluid is touching a solid surface, the temperature will be the same, like how velocity was the same. Which I've just restated this sentence up here. So the temperature of the fluid is always the same as the surface where it's contact, just the same with velocity. Okay. So both of these boundary conditions together, no slip and no jump conditions, are going to give rise to what is called boundary layer. So we talked about this a little. The boundary layer is where we have this reef of slower moving fluid particles because there's a plate there slowing down the fluid velocity. So we have our slower moving fluid particles due to the existence of the plate. All right, so if you remember the fluid touching the plate has zero velocity because the plate is at rest. And particles are going to slow down the other particles that are next to them as they're touching. So we essentially have this layer of particles at the plate that are not moving at all, and they kind of slow down the particles next to them. And as you get further away from the plate, the particles are less affected by those slow ones close to the plate. All right, and so we end up with this boundary layer. Delta is what's called the boundary layer thickness. All right, and so this is just, it's going to be a factor of X. So it will depend on how far along the plate you have gone, what the height of this boundary layer is. All right. I'm going to add a little more detail to this picture of the boundary layer. So what a boundary looks like changes the flow is laminar or turbulent. okay? And so if you have a plate with a uniform flow coming into it, you'll start off with a laminar boundary layer. It will transition to turbulent, and then you'll see that the profile, the boundary layer thickness gets larger, and then in the turbulent area, our velocity profile is approximately uniform again, right? So that just kind of connects back to when we were talking about internal flows. If you remember, we checked the Reynolds number, and then if it was turbulent, we gave that velocity correction factor was 1 because we could assume that we went flow reference speed. You can kind of see this in here too. All right, so that's the velocity bound layer. We develop a very similar concept to this, but when we talk about heat transfer, we end up with thermal boundary layer. So here, kind of the shape of what this profile looks like is a little bit different, but the concept is generally the same. What we have here is we have thermal boundary layer thickness, so that's delta sub T, T for thermal. So this is our thermal boundary layer thickness. All right, and so just like with the nip slip, the same thing happening here. So we have fluid coming into our plate hot. Okay, so we have given some temperature that is greater than the surrounding fluid that's flowing over it. And we know that our fluid, wherever it's making contact with our surface, has to have the same temperature. And so this is maybe intuitive, but you can imagine that if you have a hot plate and air flowing over it, the air right next to the plate is going to be the same temperature as the plate, and then it'll slowly cool off as you get further away from it, right? And so this thermal boundary layer thickness basically just draws the line where the fluid is 99% of the far away fluid temperature. All right, so this is, you know, the distance away from the plate where you've returned to your upstream temperature. I can use two ideas together into this plot. So here I have my plate at the bottom, and it's a hot plate. So I can draw on here, this is our boundary layer thickness. Due to the no slip condition. All right, so you'll see that it changes shape based on whether it's in the laminar region. So laminar is this shape here, and then it transitions in this little dotted area and then turns to turbulent and takes on this other here, like we saw in the other picture earlier. And then connected to that is our convection heat transfer coefficient. So this is our convective heat transfer coefficient. And you'll notice that it does different things depending on whether the flow is laminar in transition or turbulent. Okay, so this illustrates how H is not a material, it's the same fluid flowing over this plate in the whole problem here. What's changing is the flow transitioning from laminar to transition to turbulent. All right, and so we'll see that our convective heat transfer coefficient changes. Okay, so I'm just going to quantify a few things here, comparing and contrasting velocity boundary layers and thermal boundary layers. So the condition that we have at the boundary layer thickness is the following. So at the boundary layer, so at y equals delta, we have the condition that the velocity at y equals delta divided by the free stream velocity is 99%. So we're just saying that at the boundary layer, our velocity has reached 99% of what it was before it got to the plate. All right. Similar idea for the thermal boundary layer. So we have that the temperature of our surface minus the temperature of our fluid at the boundary layer divided by temperature of the surface minus the temperature of the surrounding fluid is also 90%. This is just another way of stating that when you're at the boundary layer thickness for a thermal boundary layer, your temperature is 99% of what the far away fluid temperature is, T infinity. Okay, at the surface, for a velocity boundary layer, we would define something like a surface shear stress. So this is just viscosity times the gradient of velocity at the surface of the plate. The analogy to this is Q dot at the surface, and this is minus K partial T partial Y at Y equals 0. Okay. There is a coefficient that is important for both the velocity boundary layer and the thermal boundary layer. We didn't talk about the velocity boundary layer coefficient in this class. It comes up in intermediate fluids. If you take next, but it's coefficient. When you're working on your design, independent research, you might see this come up. And it is defined to be the shear stress at the surface divided by rho U infinity squared over 2. All right, and then for a thermal boundary layer, this coefficient is just the convective heat transfer coefficient, H. So this is Q dot S divided by TS minus T infinity. So far, so good? Okay. Now, I've already mentioned a few times that the heat transfer coefficient for convection is going to depend on what the flow is doing. And so what is traditionally done is we're going to use 3 important non-dimensional numbers to help us find what H. And so I'm going to just recap those now. So the first one is the Reynolds number. Hopefully that is pretty intuitive for why we would need to know that to figure out what H should be. So if we go back and look at this plot, whether we're laminar or turbulent makes a big difference. The Reynolds number is how we decide that. So we're going to use the Reynolds number, which we've seen before. So this is going to describe our flow regime. So it'll help us classify whether our flow is laminar or turbulent, for example. All right, or if it's in transition. I'll make a small note here like I did before. Your critical Reynolds numbers are going to depend on whether it's an external flow or an internal flow or what the body is. So the 2800 that we were using for pipe flows, that's not the same as what you would use for a plate. Okay, so just keep that in mind. The next number that we're going to care about is the Prandtl number. And this number is a ratio of the viscosity over the thermal diffusivity. So this is our viscosity, which you can think of as momentum diffusivity. Divided by the thermal diffusivity. All right, and so this is essentially a ratio of a different color here. how easily momentum moves through the fluid. How easily heat moves through the fluid. All right, now this number is based solely on fluid material properties. And also, just to wake you guys up for a quick moment, I like to make this disclaimer. The Prandtl number comes up a lot in the research that I do because it involves heat transfer. And I tried very hard to avoid using the Prandtl number because Prandtl was a bad guy. It's named after a person. Good scientist, bad guy. He was a Nazi sympathizer. And I couldn't find a non weird workaround way. So the Prandtl number is commonly used. He was basically a legend in fluid mechanics. So I like to always make this disclaimer. We're all different facets, amazing scientist, not great person in society. So there's my disclaimer. Okay, next non-dimensional number is the Nusselt number. All right, you'll see H shows up in this one, right? So this is going to be actually important to us. And the Nusselt number gives us a ratio of the heat transfer via convection over the heat transfer Okay, so if you remember, convection is going to kind of lump together both the advection and convection that's happening in this moving fluid. K is only for conduction, so that's purely a material property. All right, so that's forgiveness. So tunnels, we know that convection depends on a few things. It depends on the regime of the flow. So whether it's laminar or turbulent, it depends on the material property of the fluid. And it also depends on the geometry of the surface. Okay. So essentially what we're going to do is we're going to use these three non-dimensional numbers to inform what heat transfer coefficient convection should use. Okay, so we are going to start with, we're still, if you remember, in our external flows unit. So the first geometry that we are going to care about is flow over plate. Right. That's really sick. Often does a flat plate ever actually matter to me? It can be a lot of different scenarios actually in engineering where we can approximate things as flat plates and it does a pretty good job for us. And so it actually has quite a bit of so first kind of flavor of flow over a flat plate that we are going to do is we are going to consider a plate that is experiencing laminar flow. So we're going to stick with laminar flow for now. And the plate is also going to be assumed to be isothermal. That means it has a constant temperature. All right. For this set of circumstances, we have exact relationships that have been derived for the convective coefficient of heat transfer. The reason that they're exact is because it's laminar. Right? So the problem is able to be solved analytically. This breaks down when we move to turbulent flow, right? So what we have here is the following. So we have our plate like so. There we go. This is going to be my X dimension. And we have an incoming velocity that's uniform called U infinity. And we're going to end up with this laminar boundary there. And we were talking about boundary layers are here. Again, the stance is we have flow of a flat plate. The flow is laminar and the plate has a fixed isothermal temperature. All right, and so you'll notice that all of these expressions are a function of X, meaning that all of these things are defined depending on where you are at location-wise down the length of the plate. And so the one that's really important is the Reynolds number. So we know that the Reynolds number is defined as generally like this. The subscript X here is going to give us our length. So if you have, depending on what subscript X you're using, you can find the Reynolds number at any point along the length of this plate. All right, so if you wanted to find the Reynolds number at the very end of the plate, you would just plug in X, for example. Okay, so let me just write that down. So this subscript indicates what variable to use for the characteristic length scale. All right. And we'll have some practices with that if this is not clear just yet. Okay. The one that I really want in here that I want to draw your attention to is this one. All right. So essentially to start heat for, and so we can get H by solving this equation. So we're going to solve for H. All right, and when we do that, we get over X times 0.332, Reynolds number to the 1/2, Prandtl number to the 1/3. If you recall, K is a material property. Reynolds number, we can figure out based on the density of the fluid, the viscosity of the fluid, the free stream velocity, and what position along the plate we care about. And then Prandtl number is also a material property of the fluid. So we can sort this with not even information, okay? So just a little note here. So when solving heat transfer problems, we generally need H. We have Nusselt number is H times over K. And this is equal to 0.332, Reynolds number to the 1/2, Prandtl number to the 1/3. We can solve this for H, where we have H is equal to X, K over X, 0.332, Reynolds number to the 1/2, oops, Prandtl number to the 1/3. Okay. So subscript X. Okay, so cap, these are all of the spatially varying definitions. Also have expressions for average quantities. All right, so this is going to be an average over the entire surface area of the plate, for example. And so we're using bars over each of the quantities to denote that it's the average. These look the same as we had before, except for you'll notice that there's no X in here anymore now. Reynolds number is going to depend on the entire of and then this X also becomes the length of the plate. Okay. All right. So everything above this line, this is laminar. Everything below here is for turbulent flow. All right, so still dealing with that plate still is at a fixed temperature, still at but if it's turbulent, now we need to use empirical relationships instead based off of experiments. All right, and you might be asking yourself, how do I know if it's laminar or turbulent? And I will tell you now. So the Reynolds number for determining if the flow is turbulent or not is, it has to be higher than 5 times 10 to the 5th. All right, so the first step you're going to want to do is you're going to calculate the Reynolds number for your plate. If it's greater than 10 to the 5th, you're going to use the expressions that I'm going to talk about in just a second. If it's lower than that, then you can go ahead and use the laminar ones. Okay. So just like before, these expressions are the locally varying ones. So these, or spatially varying ones. All right, so X again. I'm going to take this last expression that tells us the relationship between the Nusselt number, the convective heat transfer coefficient, Reynolds number, and Prandtl. Oh, sorry, Owen. What's up?
What was the
Good question. That is something that's kind of up for debate. It will kind of vary, like people's opinion on it. I don't have generally there aren't specific like transition relationships like these to use. So you would effectively okay, let me reapproach this question. So this relationship here, it varies with respect to X. So these relationships are kind of baked in the laminar to transition to turbulent shape into their empirical correlation. It's not going to be perfect. You know, it's based off of experiments, but it does a decent job. So this will take into account all of that. Or in just a second, to show you an averaged kind of version of this equation, which is going to take into account everything, so it'll take into account the laminar to mixed to turbulent. Does that make sense?
So, kind of, so if we have to use if problem asks for like something in the transitional phase, we would use turbulent equation. Or could we just do that?
So anytime the Reynolds number is greater than 5 times 10 to the 5th, use these. If it's not, then use the laminar ones.
Okay, so it doesn't matter if it's actually laminar flow, turbulent flow, or transitional.
Right.
The Reynolds number is, if it's greater than that or less than that, you just that is what.
Right, yeah, so we kind of classify it in sort of a binary way, even though there are 3 kind of zones.
Yeah.
Typically, this 5 times 10 to the 5th is going to capture the transition. So once it starts to become clearly not laminar, we're going to. Okay, that's an excellent question, though. Thank you for asking. Okay, so just real quick, I'm going to take this last expression and just like how I did before, for H, because that's what we're going to be most interested in. So we have K over X times 0.0296, Reynolds number at the location X to the 4/5 times Prandtl number to the 1/3. All right, so this is the utility for us. All right, and then we also care about what's happening on average. So if we care about what's going on for the whole plate, we'll need these averaged values for the friction coefficient and the Nussel number, for example. And so obviously, if we're going to average the entire plate, it's transition from laminar to turbulent, so it's going to include all of that. So that's the mix. It looks like this. So we put the bars over the CF and the Nussel number to indicate the average. And then in this case, we're going to solve for H bar. So we get K over L times 0.037, Reynolds number based on the length of the plate to the 4/5 minus 871, Prandtl number to the 1/3. All right, and again, this is the equation that has the most utility for us in this unit. Okay, so and I promise we're going to do examples that use these expressions. Cases that we want to look at first. So now we're going to look at a plate that has a uniform work. All right, so it has a constant Q dot at the surface. Just like before, we're going to break this down into if the flow is laminar over it or if the flow is turbulent. And before I do that, so what this means is instead of the plate having a constant temperature, now it has a constant heat flux. Okay. All right, so if the flow is laminar, again, we're going to use that same 5 times 10 to the 5th Reynolds number cutoff. So RE is less than 5 times 10 to the 5th. We will use this expression, so I can solve this for H. Times 0.453, Reynolds number to the 1/2, Prandtl number to the 1/3. And then if the flow is turbulent, so if the Reynolds number is greater than 5 times 10 to the 5th, we will use this expression. So we can solve this for H of x as well. So we have k over x times 0.0308 rex to the 4/5 Prandtl to the 1/3. Okay. All right, so that is our first geometry that we care about. So for flat plates, we can handle an isothermal plate with laminar or turbulent flow over it. And then we can also handle a plate with that is a heat source. So it has a heat flux coming out of it for both laminar and turbulent. Okay, the second geometry that we are going to care about is flow past a cylinder. All right, so we're going to look at the same sorts of correlations, but now instead of flow moving over a plate, it's going to move over a cylinder, just like this. So a cylinder, flow past a cylinder, the cylinder is kind of in or out of the page. So this is just our cross-sectional view here. We're still going to develop a boundary layer around the cylinder, but it looks a little bit different than our and so in this case, we are going to find an average Nussel. All right, where we have the average Nussel number is equal to the average convective heat transfer coefficient, h bar, times the diameter of that cylinder divided by k. And then this is equal to this expression on the right-hand side where we have a coefficient c and a coefficient m here. And what those values are depend on the Reynolds number. Okay. So we're going to use the same process as we had before. We want to solve this thing for h bar. So we have k over d, c times the Reynolds number raised to the m times the Prandtl number to the 1/3. All right, but then we need to calculate our Reynolds number in order to figure out what c and m are. All right, so we're not dividing this into turbulent and laminar. It's a little more nuanced for the case of the flow past the cylinder. And so we've broken down what these coefficients should be based on ranges of the Reynolds number instead. Okay. Okay, so to solve problems, we're going to use the following steps. The first step we're going to do is we're going to identify the geometry. Are we looking at a flat plate or a cylinder? I'm missing an E. Then we're going to determine the appropriate reference temperature and the fluid properties at temperature. So since there is a temperature gradient at the surface, right, we have a far away temperature and we have a temperature at the plate. So we need to pick our properties based on a temperature, right? The temperature is changing, so how do we do that? So what we're going to do is we are going to use film temperature. So this is just average temperature between the far away fluid temperature and the temperature at the surface. This is important. And I will just make a note that on exams, I will always give you like the table with the material properties in it for problems. I will always include the temperature S, the temperature infinity, and TF. Okay, so just make sure you're choosing TF to pick your properties, including the Reynolds number. Okay. All right, once you have your film temperature and then you've figured out what your fluid properties are at the film temperature, you're going to calculate your Reynolds number, and then based on that, determine your flow regime. So we're always going to use this temperature, the film temperature. To compute fluid properties. So these are K, rho, and mu. Those are the ones that you generally need to find. All right, then, once you have the Reynolds number and you know what flow regime you're in, then you want to identify whether you need a local or an average description of the convective heat transfer coefficient. So do you want H or do you want H bar? All right, so the problem should give you cues to which one you should need. If you're looking for something at a specific location, then you'll just want H. If you want to know something more global about the heat transfer, you would need H bar. All right, and then you're going to refer to reference tables or all those expressions that we talked about in the last several pages. All of those expressions will be given to you in the equation sheet for the exam, so you'll just have to figure out for on the okay, I thought you looked okay. Or do you guys need a break? Do you need a breather before we do an example? No? Okay. Moving straight ahead in that case. Okay, so we have air at 20 degrees C and atmospheric pressure is flowing over a flat plate at 35 meters per second. The plate is 3/4 of a meter long and 1 meter wide and is maintained at a fixed temperature of 60 degrees C. Find the steady rate of heat transferred from the plate to the fluid. All right. So I am going to draw a picture. So here's our plate. Not to scale. All right, so I'll use the dimension-wise description. And our width is option. And we have our ending fluid here. So this is air. We have T infinity is 20 degrees C. U infinity is, so we have an isothermal plate. All right, so our plate at a constant temperature. And we want to find the steady rate of heat transferred from the plate to the fluid. So what we are looking for is Q dot. Okay. Okay, so our governing equation is just our Newton's law of cooling. So we have Q dot is equal to capital Q divided by A, which is equal to H times TS minus T infinity. We are looking for Q dot. All right, so we want to find this, but we already know a whole bunch of stuff about this problem. So we know the plate area, the surface temperature, right? So the name of the game is 8. Right? And all these problems will boil down to this. So our first is we're going to identify the geometry. All right, so we have like, that's obvious. The next thing we're going to do is we're going to find fluid properties at the film temperature. So that is our TF. So TF is equal to TS plus T infinity divided by 2, which in this case is 20 plus 60 degrees C divided by 2, which is 40. All right, so we are going to look up properties of air at 40 degrees. Okay. When we do that, we get the following. So it's 1.127 kilograms per cubed meal. Our viscosity is 1.918 times 10 to the minus 5 kilograms over meters times second. And K is 0.02662 watts per meter Kelvin. Okay, so these are our properties. Okay, the next thing I'm gonna do is we're gonna calculate our number. So I'm gonna find the Reynolds number at L. So I have rho times U infinity times L divided by mu. 1.546. This is greater than 5 times 10 to the 5th. So that this is turbulent. All right, so we have an isothermal plate and the flow is turbulent, really narrowed down. The last things that we want is we want to figure out if we want locally varying or bulk properties. What do we think? Want to know what the steady rate of heat of the entire plate, so we're going to use properties. Okay, cool. And then our last step here is give that a since we want a bulk flow, we're going to expect mixed flow over the. All right, so when the flow is at the very leading edge of the plate, it'll quickly transition into turbulence. Okay. So let's go and find the core use. All right, so here's our section for flow over a flat plate. It's iso, but it's not laminar, so go with. So here's our isothermal flow over flow. Something local means something for bulk, and it's going to be a mixed flow. So we are going to use this. And I'm just going to copy it down over. Okay, here is our governing equation. We already found Reynolds number, but we still need our Prandtl number. So if you recall, Prandtl number is mu over alpha. Mu is just mu divided by rho. So we have properties at our disposal. And then alpha is K divided by rho E. CP is also a material property. typically on an exam, I will give you alpha directly. Just so you don't have to do all those calculations. Okay, and when I compute all of this, I get a value of 0.7255. For air, Prandtl number is generally always around 0.7. So if your problem on homework or an exam and it's air and you calculate a Prandtl that is very different from that, go back and check your work. All right. Okay, so now we have Reynolds number and we have Prandtl number, so we can go back here and solve for H bar. So K is 0.021. The length was given to us as 0.75 meters. 0.037 number, which is 1.542 times to the 6. We calculated that value is to the 4/5. And then back 871. And we multiply that whole as a number, 0.7255 raised to the 1/3. Okay, and that gives us 77.5 watts per meter squared Kelvin. So the hard part is done, but we're not finished just yet. So we still need to find Q dot, which is H bar times TS minus T infinity times the area. All right, so I'm just solving this equation. All right, all I've done is move the A over to the right-hand side. All right, and so I'm going to plug in all the things that we now have. So we have 77.5 watts per meter squared Kelvin, 60 minus 20. Recall this is in degrees C, so we need to, we don't need to do anything because the temperature difference in Celsius versus Kelvin is the same. If it's Fahrenheit, it can 0.75 meters times 1 meter. This is our area. Okay. And this is 2,035, oh my gosh, 2,325 watts. And that is our final answer.
Question about.
Yeah.
So.
Yes.
You said.
So little is that per area.
Yeah.
Yep. Fair question though. Other questions on this? What do we think about it? It's not too bad, right? So there's no rest. We're not having any, literally just algebra. Truly the hardest part of again problem. Choose the right temperature to find and then make sure that you're using relation. In this example, we have air flowing perpendicularly over a thin conducting wire. So I'm going to draw our, oh, that is the highlighter. I'm going to draw our thin conducting wire like so. And then our air is flowing perpendicularly. So that's what this means. All right. The air is at atmospheric pressure and has a temperature of 25 C. So that means our T infinity is 25 C. And it's flowing at 50 meters per second. So U infinity is 50 meters per second. The wire has a diameter of 3.94 times 10 to the minus 5 meters. So it's a pretty thin wire. and has a surface temperature of 50 degrees C. We want to find the rate of heat transfer per unit length. So we want to find Q dot divided by L. Does that make sense? Okay. Any questions on the setup? All righty. So let's start with our governing equation. So we have Q dot is equal to capital Q divided by A. And I can rewrite A as pi times dl. So A is our surface area. So we have the circumference of our circle times the length. That would be our surface area. And this whole thing is equal to H bar times TS minus T infinity. All right, since we want to find Q dot over L, I'm going to move pi times D over to the right-hand side and then replicate the rest of it. Okay, so this is our governing equation. We know T infinity, we know TS, we know D, we know pi, of course, and as is the case with all of these problems, we need to find H bar. Okay, so let's set up our steps for finding H bar. First thing we're going to do is we're going to determine oh goodness me. I'm not having a good day talking and writing at the same time. Determine, there we go, the geometry. So we have flow past a cylinder, right? All right, the second thing is we're going to determine our fluid properties at the film temperature. All right, TF is just the average between the surface and the far away temperature. So we have TS plus T infinity divided by 2. So here we have 50 plus 25 degrees C divided by 2, which is 37.5 degrees C. At that temperature, we have that nu is 16.7 times 10 to the minus 6 meters squared per second. K is 0.0270 watts per meter Kelvin. And the Prandtl number is 0.706. So like I said, if you get something that is different than 0.7 and it's air, reconsider. Step 3 is we want to find the Reynolds number. So we're going to find our Reynolds number based on the diameter D because it's a cylinder. So we have rho times D, U infinity over mu. This is just 1 over nu. So I can rewrite this as D U infinity over nu. All right. So that means that our Reynolds number based on the diameter is 3.94 times 10 to the minus 5 meters times 50 meters per second divided by 16.7 times 10 to the minus 6 meters squared per second, which is 118. Okay, remember when we were looking at the tables for flow past a cylinder, we're not actually going to determine like whether it's laminar or turbulent. We have a table of coefficients and we're going to use this Reynolds number to figure out which coefficients to use, okay? So the fourth thing is we want to find out if we need bulk or locally varying coefficient of heat transfer. So do we need a bulk or varying coefficient of convective heat transfer? I kind of already gave it away. We need H bar. Right, so we care about the total heat transfer per length. We don't care about what the heat transfer is at a specific place. All right, so we're gonna go with bulk. All right, so now we're going to find the correlation we need. All right, so I am going to go back to find our correlations for cylinders that are isothermal, which is right here. So I am just going to copy this. All right, so here is our correlation. All right, I'm going to solve this for H bar. So we have K over D times C, Reynolds number based on diameter raised to the M power, Prandtl number to the 1/3. Okay, so we have that the Reynolds number is 118, which means that I'm going to use this column of our chart. So this is the column for Reynolds number between 40 and 4,000. So that means that C is 0.683 and M is 0.466. All right, so I have that H bar is equal to K, which is 0.0270 watts per meter Kelvin, divided by our diameter, which is 3.94 times 10 to the minus 5 meters, times C, which is 0.683, times our Reynolds number, which is 118, raised to M, which is 0.466, times our Prandtl number, 0.706, raised to the 1/3, which is, when we calculate this, 3,854 watts per meter squared Kelvin. All right, we found H bar, but we're not quite done yet. So we need Q dot over L. So this is the expression I already wrote down before. We have pi times D H bar TS minus T infinity. And all we need to do now is plug in all of that stuff. So pi times 3.94 times 10 to the minus 5 meters, 3,854 watts per meter squared Kelvin, times 50 minus 25 Kelvin, gives us 11.93 watts per meter. Pretty similar to the other one, right? Any questions or concerns about the process? Yeah, Owen.
Not really about this question, but.
Yeah.
So I guess for step 4, in this example in the last one,
Mhm.
since like we're looking for that,
Yeah,
it would be bulk, but our, so for variant, it would specify like, maybe like over, you know, like where L is equal to 3 or something like that.
right. Like, so an example of like how it might change, like the phrasing of the problem would be find the difference in the rate of heat transfer from the back of the plate compared to the nose of the plate or the middle of the plate. Like it would reference a very specific location. Does that make sense?
Yeah.
Okay. Okay, cool. So these are the 2 examples that I have for external flows. They're all kind of variations on this theme. So in case you didn't pick up on the pattern already, essentially the problem boils down to finding H. So find the right correlation to find H, and then solve the Newton's law of cooling equation. And that's pretty much it. Okay. Okay, so let's switch now to internal flows. So this is going to reference some stuff from the 2nd or the 6th topic that we've already talked about that was on internal flows. So things like pipes and ducts. So we've already kind of talked about this, but inside of pipes, we develop boundary layers as well, just like we do on a plate, but it's kind of like wrapped around and in on itself. In pipes, what happens is where that boundary layer is developing and up until the point where the boundary layer kind of meets with itself from the top, is considered the hydrodynamic entrance region. So that means that our velocity profile is changing as we move down the pipe. And then eventually you'll reach a point down the pipe where that velocity profile is no longer changing. That's called the fully developed region. All right. So just to be very specific about this, when you're in this kind of region, this is called the entrance length. The flow is not yet fully developed. All right, so this description, and then in this region, the velocity is no longer changing. In the bulk flow direction. So this is fully developed. Okay. That's kind of old hat at this point, hopefully. So that is the sort of velocity boundary layer discussion for a pipe. And just like how we made an analogy with the velocity boundary layer for a flat plate and the thermal boundary layer for a flat plate, we can do that exact same thing with internal flows. So our pipe is also going to develop a thermal boundary layer as well and have a thermal entrance region and a fully developed region, just like it did for the velocity. So here, what we're seeing is the temperature profile. So if we have a cooler fluid going into a pipe with heated walls, essentially we'll have at the entrance of this pipe, the profile for the temperature will be changing up until a certain point where it becomes fully developed as well, but just thermally speaking. All right, so in this fully developed, thermally fully developed region, our temperature profile does not change in the direction of the flow. All right, so this is thermally fully developed. Okay.
Just a question. Is
Yes.
this the last bit of information that will be on the file, or do you have another packet?
This is the end.
Okay.
Is that a smile of relief or are you sad?
Well,
You don't have to lie to me, it's okay.
I'm a little happy.
Yeah, all the new stuff on the final is the heat transfer stuff. So, on Wednesday, you'll see a practice exam. I think I typically do, trying to remember, I have to remind myself what I typically do on the final. Usually I'll do like 4 questions and it'll be like a integral analysis question, a differential analysis question, and then like 2 heat transfer ones or something like that.
We'll have the full, is it like just 3 hours, like a normal?
I think it is 3 hours, yeah.
Okay.
Yep. Okie dokie. All right, so it's often useful to define a mean fluid temperature, or sometimes called a bulk temperature. That's going to be called T subscript M at a given cross section in the pipe. So the way we would define this temperature is the following. So we would take, it's 2 divided by the average velocity times the radius of the pipe squared times the integral from 0 to R of the temperature profile, which is going to depend on the radius, times the velocity, which also depends on the radius, R dr. And then we can also define a bulk temperature, which is just going to be the temperature at the inlet plus the temperature at the outlet divided by 2. All right, the mean temperature is defined by a uniform temperature distribution with the same thermal energy transported by the temperature gradient, which is a mouthful. But we can write this by using this expression for Q dot. So we know that we can define Q dot in this case as the mass flow rate times the heat capacity times Tm. So this means that we have m dot Cp Tm is equal to the integral from 0 to R of rho Cp, the velocity, which is a function of R, times the temperature, which is a function of R, 2 pi R dr. So another way that we can write Tm is the following. So we can use 2 over the median velocity R squared, integral from 0 to R, UR, TR, R dr. Once we have that median local temperature, we can solve for the local heat flux using Newton's law of cooling. So this is the same one that we've been using. Looks like that. But we still have H in here. We still need to find H. So just like for external flows, we need to find a correlation to determine what H should be. And so we divide this just like how we did for the plates, and then the flow over a cylinder. We're gonna break it into first fully developed laminar pipe flow. All right, so fully developed and laminar. So the average Nussel number for a pipe with a uniform flux. And what I mean by that is we have our pipe. So we have flow coming in and it's laminar. And we have a heat flux coming into the fluid. So it's coming from the pipe walls into the fluid like this. So this is Q dot S, and this is a uniform fixed constant value. I guess I'll draw the arrows everywhere so it visually looks like it's the same everywhere. Okay, so it looks like that. So imagine that you essentially have a pipe wall that's delivering heat at a constant rate to your fluid. Just like how we did before, this equation, we're going to solve for h bar. So we have h bar is equal to k over d times 4.36. So this is our uniform heat flux. And then we also have a correlation for laminar flow for a pipe held at a uniform temperature. So now the fluid is being heated because the walls of that pipe are held at a constant temperature. So this is again still laminar. And then this is TS, which is uniform and fixed. All right, and then again, I'm going to solve this equation for h bar. So I have h bar is equal to k over d times 3.66. All right, so far so good. Okay, now we might want to consider turbulent pipe flow. All right. And this first one is with a uniform temp at pipe wall. So this is our isothermal pipe. So in this circumstance, we have our pipe here, and then this is how I'm going to draw turbulent, I guess. All right, and then this wall is uniform and fixed. Constant temperature TS. We're going to solve this expression for h bar. So I have k over d times 0.023 Reynolds number to the 4/5 Prandtl number raised to n. You'll notice that we have a coefficient on the Prandtl number n. We're going to use a value of 0.4 if the fluid is being heated. So if the surface temperature of our pipe wall is greater than that of the fluid flowing through it. And then we're going to use a value of 0.3 if the fluid is being cooled off. All right, so if the temperature of the fluid in the pipe is hotter than the surface temperature of the pipe walls. Okay. Okay. The other thing that we want to make note of is how we will evaluate our properties of our fluid. So we're going to use this expression here. This is the analogy, or this is analogous to the film temperature for external flows. All right, so we're going to take the TM value at the inlet, add it to the TM value at the outlet, and divide by 2. Okay, let's do an example that is also kind of going to serve as a derivation. So this is an example, I'm calling it an example, but it's not really an example. It's just kind of like a guided thought experiment derivation. So this isn't something that you would see on homework or the exam, just for full disclosure. Okay. So we're going to consider steady flow through a pipe with diameter D and length L. The inner surface of the pipe is maintained at a constant temperature Ts. And then we're going to let the mean fluid temperature at the inlet and outlet be called T in and T out. All right, pretty standard. So for this system, we want to find an expression that describes Tm as a function of X. All right, so let's draw a picture. So I have a pipe that looks like this. So we have flow coming in, flow coming out. And then I'm going to consider a little differential element of our pipe. So this is a length dx. And at the inlet, I have Tm, and at the outlet, I have Tm plus dTm. So like a little elemental amount more. So our governing equation is Q dot is equal to M dot Cp T in minus T out. But what we want to find is Tm as a function of X. So we're going to do the following. We're going to apply conservation of energy to a differential element in the system. And that's what I've just drawn to the right. That guy. All right, so conservation of energy tells us that E dot in is equal to E dot out. Energy in is equal to energy out. That's conservation of energy. And we can write this as M dot Cp times Tm plus dq, because we have that little element of heat transfer coming into our system, is equal to M dot Cp Tm plus dTm. So this is our energy out. You'll notice that I have an M dot Cp Tm on both sides of this equation. So I end up with dq is equal to M dot Cp dTm, which hopefully makes sense. The little bit that it's been heated from the beginning to the end is going to be equal to what we have put into the system, right? Okay, so I'm going to call this equation star. All right. Now I'm going to consider the case where we have constant surface temperature at the wall. All right, so Newton's law of cooling is just dq is equal to q lowercase q dot dA, which is h times ts minus tm dA. And then I can rewrite this dA given our geometry. So I have pi times d dx. All right, and I am going to, so this is dq. I'm going to put a box around this equation and I'm going to call it star star. And now I'm going to set star and star star equal to each other. So I have m dot cp dtm is equal to h times ts minus tm pi d dx. I'm going to divide through by dx to get a differential equation. And I'm also going to move, so I'm going to move this over to the right-hand side, and then I'm going to move this over to the left-hand side. All right, so when I do that, I get dtm divided by dx is equal to h over m dot cp pi d ts minus tm. We want to find an equation for Tm as a function of x. So this differential equation is essentially what we need. We just need to solve it. But first we're going to do a little rearranging to make that a little easier for us. So what I'm going to do is I am going to say that the differential of minus ts plus tm dx is just dtm dx, because the surface temperature is a constant. So if we take the derivative of it, it's just 0. All right. So if I put that into my system, I have minus the differential of ts minus tm divided by dx is equal to h pi d divided by m dot cp ts minus tm. All right, I'm going to separate variables and integrate. All right, so I have minus dts minus tm over ts minus tm is equal to h pi d over m dot cp dx. All right, so this is why we did that like convenient thing with adding the ts inside the differential, just to make the integration a little simpler. All right, and I am going to evaluate this between delta T in, delta Tx. All right, and so just to make this abundantly clear, delta T in is equal to Ts minus Tm in. And then this is equal to Ts minus Tm of x. Okay. All right, so when I do this integration, I get minus natural log of TS minus TM evaluated from delta T in to delta T of X is equal to H pi D M dot CP times X. Any questions so far?
Oh. How did you go from DX to TS minus TS when you first started?
Do you mean from here to here?
Like, I guess, if you know, so like after you rearrange them, you had, negative D, TS minus TM over DX.
This guy? Yeah.
Yeah, and then you changed it, and DX turned into TS minus TM. below it.
Oh, I just separated variables. So,
Oh, you-
yeah, so
Oh,
this is
okay.
like my variable that I kept with this differential.
oh,
And then I moved dx over here.
I must have- I must have-
No, it's okay. It's all good. We honestly could have just like left it in this form, and separated variables and integrated, it would have been fine. This honestly, what I've shown to you here is like the alternate version of a U substitution. So yeah, maybe next time I teach this, I'll just do it the regular way.
Well, it all makes sense. I was just hopping from one thing to another, and I just,
No, it's totally fine. Okay, so let's evaluate the left-hand side at these limits. So I have minus natural log of TS minus TM at X plus natural log of TS minus TM at the inlet is equal to H pi D over M dot CP times X. I can use a law of logs. So if I have natural log of A minus natural log of B, this is natural log of A divided by B, right? So I'm going to utilize that to turn this left-hand side into the natural log of TS minus TM at the inlet divided by TS minus TM of X, which is equal to our same right-hand side that we are carrying around here. H pi D over M dot CP times X. I'm going to exponentiate both sides. Right? And I get TS minus TM at the inlet divided by TS minus TM at some position X is equal to E to the H pi D over M dot CP times X. And now I'm just going to solve for TM. All right, so I have TS minus TM of X is equal to TS minus TM in E to the minus H pi D over M dot CPX. So we have TM of X is finally equal to TS, oops, minus TS minus TM at the inlet e to the minus h pi d over m dot cp times x.
Fixed pieces.
Oh, yes, sorry. Sometimes I write it that way if I feel like it's like too much stuff to squeeze into a little exponent. Should have kept it consistent though. Sorry. Yeah,
Would you be able to rewrite that as just like, positive TMA e to the negative h pi d? Because the TS and then you can like distribute the other side to it. Like the parentheses and then it would be like TS. Or
so yes, you could rewrite this. I think this is what you mean, but here, let me just make sure. So this would be, oop. You would have TS 1 minus the exponent plus T m in exponent. Is this what you mean?
maybe I was just thinking about, not that, but the, so if the quantity of TS minus TMA
Mhm.
is raised to that exponent,
Oh, no, no, no. No, no, no. So it is,
or is it, it's e to the exponent?
yes.
Okay.
So here, let me. So this is. Does that help?
Yeah.
Okay. Okay. The second case would be if the pipe supplying heat to the fluid inside of it was supplying a uniform heat flux. So that is, now we have constant Q dot S instead of, oops, TS, okay? I'm not gonna do that derivation. I'm gonna skip it. And the result is the following. So we get Tm of X is equal to Tm in plus Q dot S pi times D over M dot CP times X. It's simpler. Okay. All right. So let's read this example together. So we're going to consider a very hot day in Arizona where the ambient temperature is 110 degrees Fahrenheit and there's a steady breeze at 5 meters per second. So the first part of this question is if the starting temperature of the pavement is 160 degrees Fahrenheit, what is the net rate of heat transfer to the ambient air? Okay. Oh, and sorry, one small additional detail. Assume you are considering a 1 meter by 1 meter square of pavement. Okay. Okay, so let's draw a picture. So here's our pavement. We have a surface temperature TS of 160 degrees F. We have flow going over top with T infinity is 110 degrees Fahrenheit. And U infinity is equal to 5 meters per second. And for reference, 110 degrees Fahrenheit is 344.26 Kelvin. And 160, sorry, that's wrong. I did this backwards. This one, 110 is 316.48 Kelvin. And 160 is 344.26 Kelvin. Okay. So, first step is we want to figure out our geometry. What kind of geometry do we have, you guys? It's a flat plate. Yes, lovely. Alrighty. And the second thing we want to do is we want to find our fluid properties at the film temperature. All right, so our film temperature is 160 plus 110 degrees Fahrenheit divided by 2, which is 135 degrees Fahrenheit, which is 330 Kelvin. All right, third step is find rho, mu, Prandtl number, and K at TF. You would be provided with a lookup table to do this. And when you did that, you would find that rho is equal to 1.086 kilograms per meter cubed. Mu is 1.962 times 10 to the minus 5 kilograms per meter second. Prandtl number is 0.701. And K is 2.816 times 10 to the minus 5 kilowatts per meter Kelvin. All right, next step is we are going to calculate the Reynolds number. So the Reynolds number is rho L U infinity over mu. So we have, when we calculate this, we get 2,300. And this is less than 5 times 10 to the 5th. So this is laminar flow. All right. Our next step is we want to find the correlation. All right, so we're looking for a flat plate with laminar flow and a fixed temperature on the plate. We can go all the way back to the beginning here. More. Okay, so laminar flow over an isothermal plate. Do we need bulk or varying properties, do we think? Yes. So we are going to use this one here. So we want to find H. So we're gonna use that. Okay, so we have that, oops, we have H bar is equal to K over L 0.644 times our Reynolds number to the 1/2 times our Prandtl number to the 1/3. So we're gonna plug all this information in. So we have 2.816 times 10 to the -5 kilowatts per meter K. I'm actually gonna change this. I need this in watts, so I'm gonna make this not kilowatts anymore. So this is actually -2 watts per meter K. Divided by L, so we have our 1 meter. And then Reynolds number was, where was it? 2,300. Oh, wait, sorry, we need this 0.644. 0.644 times 2,300 to the 1/2 times our Prandtl number, which was 0.701 to the 1/3. All right, and this gives us that H bar is 4,446.3 watts per meter squared K. So we have found H, that's good, but we need to plug this into Newton's law of cooling to figure out our Q dot value. So we have Newton's law of cooling is little q dot, which is capital Q dot over A, is equal to H bar Ts minus T infinity. All right, and so we get that this is equal to 446.3 watts per meter squared times Kelvin times our temperature difference is, where'd it go? 344.26 minus 316.48. So this is Q dot. And we get 123,518 watts per meter squared. So Q dot is equal to little q dot times A. So we have 123,518 watts per meter squared times 1 square meter, because we have a 1 meter by 1 meter square. So we still get 123,518 watts. Sound good? Okay. I really enjoy the second part of this question. I wrote this question myself. I was very proud of it. Okay. Okay, let's do part B. Okay, so for part B, you've heard that you could cook an egg on the pavement if it's hot enough. So you think you'll give it a try to see if it's possible. Assuming you can approximate the egg as a flat plate that is 1 centimeter thick, and then it has a starting temperature of 45 degrees Fahrenheit, because that's refrigeration temperature. Find the temperature of the egg at steady state. Assume that the egg has a thermal conductivity of 0.59 watts per meter degrees C. So fun, right? Okay, So let's set it up. All right, so we have our pavement. This is TS at 160 degrees Fahrenheit, which is 344.26 Kelvin. And then here's our egg. All right, and it has a thickness of lowercase d, which is 1 centimeter or 0.01 meters. 1 centimeter is kind of thick, but that's okay. All right, and we also are given that this material has a K equals 0.59 watts per meter degree C. All right, we still have our ambient conditions out here. So T infinity is 316.48 Kelvin. And H bar from part A is 4,446.3 watts per meter squared Kelvin. And our egg starts at T naught of 45 degrees Fahrenheit. Okay. Sound good so far? So this is kind of a blended problem in terms of all of the heat transfer units are going to come into play here. So we want to find the temperature of the egg at steady state. So this is essentially a conduction problem with a convection boundary condition. All right, which we kind of did in the conduction unit. Okay, so we are going to approximate as a plate. And we're also going to assume that it is 1D. All right, so I'm going to draw this picture of my egg. I'm going to call this, is anybody offended if I make this the X direction, or do you want it to be Y? I don't really care. Okay, I'm going to call this the X direction. And we have our thickness D. And then at the top, we have Q dot convection. And at the bottom, we have our isothermal condition. So we have our temperature of the surface of the pavement. Okay. So our governing equation is the time rate of change of the temperature of the egg is equal to minus K, second derivative of the temperature with respect to X, plus the second derivative of the temperature with respect to Y, plus the second derivative of the temperature with respect to Z. So we've assumed this is 1D, and we've also assigned this the X direction. So that means that I don't have any variation in Y or Z because we've assumed 1D. And then the problem also asked us to find the temperature at steady state. So that means I can get rid of this time derivative as well. So all I have left here is that 0 is equal to the second derivative of T with respect to X. Question?
There you go.
Oh, it's 0 on the left-hand side, so I just divided through. Very sneaky. Other questions? It's so nice outside, you guys. This is painful. Okay. Sorry. All right. So I'm going to separate variables and integrate this twice. So I have d time, or the differential of dt dx is equal to 0 times dx. I'm gonna integrate this integrate both sides. And I get dt dx is equal to a constant. I'm going to separate variables and integrate again. So I have dt is equal to c1 dx. Integrate both sides, and I have t is equal to c1 x plus c2. Okay, we need boundary conditions to figure out what c1 and c2 are. All right, so our boundary conditions are that T at x equals 0 is equal to Ts. So that's just the temperature of the egg at the pavement is the temperature of the pavement. And then we also have that at this is okay, so this is boundary condition number 1. Boundary condition number 2 is that at x equals d, there's a convective heat flux. All right, so I'm going to write this as minus k partial t partial x is equal to q dot, which is minus h bar t at x equals d minus t infinity. All right, so basically what I'm saying is q dot equals q dot. So the conduction q dot is equal to the convection q dot right at that surface. Just like how we did before. So when we apply boundary condition number 1, we get that Ts is equal to C1 times x equals 0 plus C2. So that means that C2 is equal to Ts. All right, and then if we apply boundary condition 2, we have minus k partial t partial x at x equals d is equal to minus h bar t at x equals d minus t infinity. So we have minus k dt dx at x equals d or anywhere is just c1. And then we have minus h bar times t at x equals d. So I have c1 times d plus ts, because that's what c2 is, minus t infinity. So let me just highlight a few things here. So t at x equals d is this. And then this is just C1. Is everybody with me so far? Okay. So now what I'm going to do is solve for C1. Oop. So I have minus k C1 plus C1 h bar d is equal to h bar t infinity minus ts. I'm going to group I'm gonna factor out the C1 from the right-hand side. So I have H bar D minus K is equal to H bar times T infinity minus TS. So C1 is H bar T infinity minus TS divided by H bar times D minus K. We have all of these values, so we can plug them in. So I have 316.48 K minus 344.26 Kelvin. Oops. I forgot H bar was first. H bar is 4446.3 watts per meter squared Kelvin divided by H, which is 4446.3 watts per meter squared Kelvin times 0.01. That's our meters. That's our thickness D minus 0.59 watts per meter degree C. Now, there's an issue with the units at the moment. We have Kelvin and then we have degrees C. So we need to convert this. To watts per meter Kelvin. And it is equal to 0.00215 watts per meter Kelvin. Alrighty. And so when we do that, we get that C1 is equal to negative 2778.12 Kelvin per meter. So we get that T is equal to minus 2778.12 Kelvin per meter, X plus 344.26 Kelvin. All right, as just a sanity check, remember at X equals 0, we're at the pavement. So if we plug X equals 0 into this expression, we get the temperature of the pavement. That's good. And then as X increases, our temperature goes down, which that makes sense because we have this cooler air blowing over top of the egg. So we would expect that our temperature of our egg is going to decrease as we go up. Okay. And then I forgot to write it in, but I was gonna say like, this is the temperature that an egg needs to be cooked to. And then you just have to calculate like what the minimum temperature of the egg is. The minimum happens at the top of the egg. So you would just have to see if that met the condition for cooked or not. Okay. How do we feel about that one? A little trickier.